Error compensation in linearized filters is an important issue because, as indicated and illustrated before, we can have problems with the nonlinear functions that they introduce biases, and we have wrong Jacobians, being just some of them. So there are a number of methods, and we'll start discussing some heuristic methods. The way we obtained the EKF was by a Taylor series expansion up to first order terms, which is really linearization, or up to second order terms. It's clear that both these filters can introduce errors in the equations where such an expansion is used due to the following facts. First one is we neglected higher order terms. Second, the evaluation of the Jacobians and Hessians being done at the estimated or predicted values. We use the estimated when we calculate a predicted state, and predicted state when we calculate a predicted measurement. So these values, the estimate or predicted states, were used rather than the exact values because they are not available. So these are already some sources of errors. What we have now is some ways of compensating. The first way of compensation is the addition of what is called artificial process noise or pseudo noise to compensate for the errors in the prediction. Effectively, what we do in this case is we use a larger modified process noise covariance Q sub m, which is an extra QP. There's a pseudo noise on top of QK, so it's going to be larger than QK. So this is a QP, a positive semi-definite pseudo noise covariance. So what this does is indicates that there are additional unaccounted for errors in the state prediction equation. The other one would be to multiply the state covariance by a scalar phi greater than 1 at every sampling time. Namely, p phi would be a phi times p k plus 1 k. So this is really a jacked up prediction, a jacked up version of the prediction covariance matrix in the covariance update equation. So again, we trust less the past data and use this fudge factor phi to discount the past data. There are other options. You could use a matrix cap phi, which is diagonal with some square root of phi i's, that obtain selectively jacked up state covariance terms. So there's a phi p phi. There's no need to transpose here because this is a diagonal matrix. So all this amounts to a fading memory, not exactly an exponential fading memory like it is done in what's called the simple alpha filters or other techniques from statistics, but what we have is a method of discounting the past data. We have a larger covariance or lower accuracy. Now, what does this increase of the covariance matrices accomplish? So we have a larger state covariance matrix and more weight to the recent data. This is a higher gain and effectively a higher bandwidth. So we rely more on the recent measurements. Conversely, increasing the variance of the measurement noise, which will increase the innovation covariance, would lower the filter gain. So it has to be added that these are really band-aid techniques, even though they are used in the real world, but they are heuristic. And they should be used only as a last resort. The flaw in them, and they are flawed indeed, is because of the assumption that the linearization errors are zero, mean, and wide. By changing the covariance only. We keep the zero mean assumption, we keep the whiteness assumption, we say the errors are large. So, in some cases that's the only thing that can be done, but one has to remember that the fundamental assumptions of the filter are there, and what we do is we compensate only for some of the errors introduced, namely the variances. Now, if we have inconsistency because of bias due to nonlinearities in the system, this method will not accomplish much. And we have to go to bias compensation, namely an evaluation of the bias due to nonlinear transformations and compensation for that. That will be discussed later. First, we'll take a quick look at what that fudge factor heuristic technique can accomplish. And we go back to that passive tracking example of a moving target on the x-axis from a platform coming in from behind. The filter really did not pass the consistency tests. So what we are going to do is use the covariance increase technique, the fudge factor technique, and we'll illustrate what does it accomplish. The fudge factor was taken as phi equal to 1.03, just a 3% increase every step. The resulting normalized state estimation error still shows some points outside the probability region that we set it at 97.5%. So it's a 95% two-sided, but it's still above the 97.5%, the upper range. And also we have still problems with the normalized innovation. And the third thing, we'll see them in a moment, will be what happens to the absolute errors, the RMS, the unnormalized errors. Do they decrease when we fix to some extent the covariance? And we'll see the answer to this question. So, first is the normalized estimation error square. Here is the upper limit, it's 95%, as the upper limit is 97.5%. On the average should be 2. Still we have a few points outside. So we reduced the number of points but didn't eliminate all of them. Look at the innovation. We still have towards the end 1 point that's out. It's not too bad. It's only 95% region. And now we look at the absolute errors, and comparing with the results from the previous one, it turns out they are not very different. As a matter of fact, towards the end, this seems to be even a little bit bigger than what we had earlier. So it doesn't necessarily mean that we solved the problem clearly. And in view of this, we will now discuss a systematic technique which, however, can be applied to a certain class of problems, not to all problems, when you have measurement coordinates as polar and the conversion will be done from polar to Cartesian. This, fortunately, can be done exactly, and it is an application that is already implemented in the real world. So here's our example of how to do a systematic compensation for the conversion from polar to Cartesian. In a typical two-dimensional radar, the measurement values of position are the range and azimuth or bearing. But the motion, as indicated before, is naturally expressed in Cartesian coordinates. So if we can convert from polar measurements to Cartesian measurements, and this is a nonlinear transformation without bias, and this is the most important thing, and obtain the correct covariance for the converted measurements, we end up with a situation where we can perform the state estimation within a completely linear framework. Measurement, the best model we can have is linear. Might not be perfect, but it's reasonably good. We have polar measurements. There might be a problem when you use mixed coordinate filter. Might be a problem if you convert using what's called a simple conversion, because we show that there is a bias, and we can also indicate in what situations you have the bias. So let's look now. We have the problem with polar measurements, and we attempt to do the standard conversion. So what we measure now is range and azimuth or bearing. Range is the true range plus the range measurement noise, WR. The azimuth theta measured is theta plus W sub theta. That's the as or bearing. Each of these noises are modeled in the polar coordinates as zero mean and with known variances sigma r square and sigma theta square respectively. What is the standard conversion? That's high school trigonometry. Xm is Rm cosine theta m, Ym is Rm sine theta m. Now, what are the covariances? In this case, using linearization, R superscript L for linearization, so the variance of this conversion is given by the impact of sigma theta square is an Rm multiplied by Rm square sine square theta m, and the impact of sigma r in the x coordinate is sigma r square cosine square theta m. So here is the x, here is the variance for the y coordinate, and here is the covariance between the x and y. Clearly, while in polar, the range and azimuth are uncorrelated. After you convert, you end up with a correlation between the x and y. So in Cartesian, we have a full 2 by 2 matrix, which is not a problem because the Kalman filter can handle this with no difficulty. The question is this conversion leading to a bias? Number one. And the second question is, do we have the correct covariance for the converted measurements? Okay, so let's look whether we have an unbiased conversion, and if not, how to come up with an unbiased conversion. Okay, the expected value of the xm, this is the converted version from polar to Cartesian for coordinate x, is going to be the expected value of Rm times the expected value of cosine theta m, because xm is Rm cosine theta m, and because Rm and theta m have independent errors. What we get here is using a simple trigonometric identity that cosine theta m, which is theta plus W theta, it's a cosine cosine minus sine sine, and because the sign of the error is zero mean, that's an odd function, turns out it is the cosine that comes into the picture here. So the expected value of the converted measurement in coordinate x is b1 times the true value. It turns out with simple examination you get exactly the same b1 multiplying the true value of y that gives the average, the expected value of the converted y. That's the expected value of ym. So what we have is what is called a multiplicative bias. And the expected value of cosine of this measurement noise, if it's w theta, with variance sigma theta squared, turns out to be a little bit less than unity. And very important that sigma theta has to be in radians. Radians is the only natural way, it's a dimensionless quantity, and the only natural way in which an angle is to be measured. For convenience, we use degrees, but when you use an exponential, you must have a dimensionless quantity here. So only radians are valid here. So with this, the unbiased converted measurements will be take the standard conversion and divide it by b1, both for x and for y. So what we have now is a way of debiasing or coming up with an unbiased version of the conversion. Now, it's very important to know when this technique, which is obviously a little bit more complicated than the technique of doing the conversion via the simple equations without compensation. When do we need this special technique? And the answer to this question will be by providing the validity limit of the standard conversion. And this will be a very easy calculation that can be done literally on the back of an envelope as follows. The bias in the two coordinates, mu x is x minus exm. Mu y, this should be a y here, is y minus eym. Each of these is the appropriate true value times 1 minus b1. So the norm of the bias can be taken as simple calculation, square root of mu x and mu y is r times 1 minus b1. The maximum bias magnitude. Now we can use a series expansion and see when do we get the largest bias is r sigma theta square over 2. We just take this, the first term, and in an expansion, this is an exponential, it's e to the minus sigma theta square over 2. So would this, and again, this should be in radians because then mu will be range, that's a linear distance or length dimension. So the maximum bias is r sigma theta square over 2, and this is to be compared to the minimum standard deviation of the measurement position in the range and cross-range directions. In the range direction, we have sigma r, the cross range is r sigma theta, because this is the distance, r the range, times the angle, and this gives the error perpendicular to the range, or the cross range error. So this is the minimum eigenvalue of the position covariance matrix. As we said, we have a full 2 by 2 matrix in Cartesian, but it's easier to go back in polar because it will be slanted in Cartesian and look at the range cross range in this case. So these are the two eigenvalues, and the smaller is what matters. So what we want is to see when this bias is becoming significant as follows. The bias significance is the ratio of these two quantities. There's r sigma theta square over 2, and the smallest between sigma r and r sigma theta. Clearly, what we have here is a situation where we have to specify how much can we tolerate. These are the eigenvalues of the covariance matrix. So these are like the standard deviation. This is the bias. So we say we will allow 20% of the standard deviation as bias. Typically, the reason for this is with 20% bias, you really don't notice the bias within the randomness unless you take a very large number of measurements. So we say that we allow up to 20% bias. So beta max, this bias significance ratio, is up to 0.2. So if we use, depending which is the smaller one, when this sigma r is in most cases will be the smaller one, so we get r sigma theta square over 2 sigma r is less than 0.2, or r sigma theta square over sigma r less than 0.4. The other case, the r cancels and we get sigma theta less than 0.4 radians, so 23 degrees, which is effectively always satisfied, so the second is irrelevant. But the first one turns out not to be satisfied in some radar systems. In most systems, we have this inequality 18 satisfied. In sonar systems, which have a large sigma theta, or in radar systems, which have a large r, even though they have a relatively modest sigma theta, and the small sigma r, this ratio can be as much as 2 or even more. So what we have is a guideline for the limit of the validity of the standard conversion, and only this equation 18 has to be checked, and that's what I meant the back of the envelope simple. Calculation indicates if a particular system needs debiasing. There are some radars with a range of 1,000 or more kilometers or nautical miles, and you end up with this ratio being significant in excess of 0.4. Therefore, there is a significant payoff in carrying out this unbiased or debiased conversion. One more thing which we'll present without derivations. Derivations are covered in the text. The unbiased conversion covariance, there are a little bit longer expressions. It doesn't matter what they are, except we know they do provide us, as we'll see in a moment, consistency of those estimates, which means the mean is 0 after we do the compensation for the bias, and the calculated covariance has to be different than the standard conversion would give you. So we'll do now a consistency evaluation. We'll show how it was done. A statistical consistency check along the lines of what we have seen for the Kalman filter. And to summarize, the procedure is as follows. For a zero mean random vector z tilde, that's the measurement error, of dimension nz and covariance p, assume this is the covariance p we calculated in one way or another, the expected value of the normalized error squared, NES, is z tilde prime p inverse z tilde, which will be on the average nz, because it is an, under the Gaussian assumption, it is an nz degrees of freedom chi-square variable. So what we have now is the sample mean of n independent realization is what we are going to use. So instead of using a single realization, we use a phi bar from n realizations. And again, this will be around nz with a narrow range, and we'll use the chi-square distribution as before to calculate the probability region in which this statistic phi bar has to fall in order to accept the hypothesis that z tilde is 1, 0 mean, 2 has covariance p. So these are the two things we are going to check now. So the mean value should be 2 if there is no bias and the covariance assumed or calculated covariance matches the actual errors. And under the Gaussian distribution assumption, we have n times a chi-square with nz degrees of freedom, in this case n times 2, if n is 1,000, 2,000 degrees of freedom, and we'll use an acceptance region based on the 2,000 degree of freedom chi-square divided by 1,000, so it is back around 2, and will vary in this case the accuracies. The first thing, we have the average normalized estimation error squared, normalized error squared, sorry, the NES normalized error square for the conversion with calculated covariance RU. This is for the unbiased conversion. The scenario that was used was the two target position was 100 kilometers away from the sensor, azimuth 45 degrees, standard deviation of the range error is 50 meters and will vary the angle measurement error. And we have the 99% probability bounds, really it's upper half percent, the lower half percent were cut off. And we'll see the standard conversion results with the covariance RL. So we see what happens if we use an unbiased and RU covariance calculated for the conversion, and the simple conversion where we ignore if there is a possible bias, and we use the simple expression based on linearization for the covariance. And here is the result based on the standard ratio of the bearing in degrees for convenience. The average of the unbiased conversion, this is the bias conversion. Here we have the figure broken down into two. This is the conventional conversion. You can see that for that particular set of parameters, when the measurement error is at 1 degree, you already have a problem. Probably up to about 0.7, 0.8, it is still okay. Starting at 1 degree, the conversion is not consistent. So this is the conventional, the standard linearization-based conversion, and here is what happens if you use the unbiased conversion. This is a 99%. Once in a while it is outside, but you can see that even at 10 degrees standard deviation for the bearing or azimuth measurement error, things are still within the appropriate probability region most of the time. I can't expect it all the time, but it's most of the time. Remember, this is a 99% region. So we have seen that error compensation in linear filters is an important topic, and linearization of nonlinear systems to obtain linear filters introduces unavoidable errors. And some of the simplest techniques to handle such errors was by increased covariances. If we add a pseudo-noise, pseudo-process noise covariance, we will increase the covariance of the state. You can also multiply the state covariance by a fudge factor slightly larger than unity. So in this case, we hope the covariance covers the error in the sense of filter consistency. The normalized estimation error squared will be within the acceptable region. The problem with this is that such a method will assume that the errors due to linearization are random. Typically, they are neither zero mean nor white, so that's a questionable technique, even though sometimes it does work. And if the errors are not random, that's a situation where we have bias. We can do bias compensation, and we illustrated the technique of bias compensation on the conversion from polar to Cartesian, and there is a very similar conversion from spherical to Cartesian when you have 3D radars and you convert to Cartesian. Sometimes you have to do bias estimation. Actually, it turns out that sensors do have biases, which we did not assume, and you have to do bias estimation for sensors in certain situations, mainly in the case where you want to fuse together the data from various sensors which are not oriented or not calibrated exactly. You can do bias estimation by adding extra state components. This is in practice for a large number of targets. This is not very convenient, but in any case one has to ascertain that an augmented state, which will be target states and bias states for the sensors, is completely observable. Not always this condition is satisfied. So there are recently developed techniques in the literature which handle such situations.